So today I'm going to be showing you another question, and this question is a classic proof that appears in most first year analysis courses. And I personally find this theorem to be really intriguing because it's a theorem that most of us will often use in high school in most of our calculus classes without actually knowing why it is true. I mean, it's intuitively, it just makes sense, but its proof is actually pretty nice as well. So let me show you what the question is. So the question is, let a and b be real numbers where a is less than b. So this is just a formality. You have to define certain intervals. So in this case, we are defining the closed interval a comma b, and the way we define it is we say that let a and b be real numbers such that a is less than b to ensure that this interval is well defined. And then we're saying that f is a function that is differentiable on the open interval a comma b, and we're also assuming that for every point on the open interval a comma b, the first derivative is greater than 0. And what we want to do is prove that f is increasing on the open interval a comma b. Okay, so first of all, let me give you some idea about where we exactly use this theorem. So for example, let's say that I'm going to show you a graph, and this is the idea behind the proof, or behind the theorem. So let's say that these are 2 points, A and B, and what this theorem is essentially saying is that for every point between A and B, if the derivative is greater than 0, in other words, the slope of the tangent line at any point is positive, then the function is increasing. So an example of such a function, for example, would be this. If you draw the tangent line at any one of these points, you'll see that the first derivative is greater than 0, which means that the slope of the tangent line is also positive, and thus the function is increasing on the open interval a comma b. It's actually increasing on the closed interval a comma b, but we're not going to go into that technicality yet. So now the question becomes over here exactly where do we use this? So this is quite often used in curve sketching, for example, whenever we need to figure out, whenever we need to draw a function, we often compute its first derivative, figure out where the function is increasing, figure out where the function is decreasing, and then plot that function. And when we do so, we often assume that the first derivative being positive is the very definition of the function increasing, which isn't really true. If you ask most high school students what does it mean for a function to increase, they'll tell you that, well, if the first derivative is greater than 0, then the function is increasing. And what I often say in such circumstances is, well, what about this function, for example? This function is increasing everywhere, but it has a vertical tangent line at this point, so the derivative doesn't even exist at this point. So, well, is this function increasing or decreasing? How do you know? And well, this function is clearly increasing, so I mean, there has to be some other universal definition of increasing that applies to all situations or all circumstances. So what I would like you to do at this point is pause the video, try to come up with the definition of an increasing function, a universal definition that applies in all circumstances, irrespective of whether or not the given function is differentiable, and then try to write a proof for this theorem. I mean, I would encourage you to, use some other theorems that you might know, or, try to get an intuitive geometrical idea about why this theorem is true before you start writing a proof for it. So, yep, pause the videos now and try this question on your own. So by now, I hope you guys have tried this question on your own. Now, what I'm going to do is I'm going to show you a proof for it. But before I show you the proof for this for this question itself, I want to emphasize on two things. The first thing is actually a lemma, or actually a proof that or another theorem that I'm going to use in order to prove this theorem. And it's actually a very, very famous theorem. It's called the mean value theorem. This is by far the most important theorem that you learn in first year. Pretty much all of calculus rests on this theorem. And what it says is that let a and b be real numbers such that a is less than b, and let f be a function defined on the closed interval a comma b. And then if f is continuous on the closed interval a comma b and differentiable on the open interval a comma b, then there exists a point on the open interval a comma b such that the derivative at that point is equal to f of b minus f of a divided by b minus a. And we are going to use this theorem, the mean value theorem, in order to prove that a positive derivative implies the function is increasing. So to give you a little bit of an idea about what this theorem essentially saying, it's something like this. Let's say that you have a graph. Let's say this is point A, this is point B, and I'm going to label these 2 points, and I'm going to draw a graph over here. Okay, so let's say this is a graph, and what this theorem is saying is that as long as this function is continuous, which it is, and differentiable, which it also is, on the closed interval a comma b and then the open interval a comma b respectively, then this must be true. So there must exist a point where the derivative is equal to, or the derivative is equal to the slope of this line. You can just join the point f of b and f of a, and while the slope of this line is f of b minus f of a divided by b minus a, and the theorem is saying that there is some other point on the open interval a comma b where the slope is equal to this point, which is clearly true because while the slope at this point, for example, is the same as that point. So there is a way to prove it, and instead of proving it in this video, I'll actually leave a link down below in the description box where one of my profs, he actually provides a pretty nice proof for this theorem, and I believe it's actually pretty well explained as well. Okay, so I'm going to be using this theorem, and one other thing that I'll be using is the definition of an increasing function. So this is how we rigorously define what it means for a function to increase. So we say that f is increasing if and only if for every x1 and x2 in its domain, we have that if x1 is less than x2, then f of x1 is less than f of x2. And this makes sense because what it's saying is that if you pick any 2 points in the domain of f, then if one of those points is less than the other point, then the value of the function at one of those points is less than the value of the function at the other point. So I mean, this would look something like this. Let's say that the domain of I is 0 to infinity, and then for example this function would satisfy it because no matter what 2 points I pick, I can pick like this point x1, I can label this x2, then the value of the function at x1 is going to be less than the value of the function at x2. And the important thing to notice over here is that this condition is satisfied for every x1 and every x2 in the entire domain, as long as x1 is not equal to x2, which of course is guaranteed by this equation. Otherwise, if x1 is equal to x2, then this condition will not be satisfied to begin with. Okay. So now that we have this, we can go about proof. Now that we have all the components, we can actually start writing a proof. So let's begin. So remember, a good proof will always begin by redefining all the variables that you are going to be using in the question. So in this case, I'm going to be using a and b. So I'll define that again. I'll say let a and b be real numbers such that a is less than b. I'll also be using the function f. So I'll define f. So I'm going to say let f be a differentiable function, or a function differentiable on the open interval a comma b. And then we're going to state all our assumptions. So in this case, we only have one assumption. We are going to assume that for every x in the open interval a comma b, the derivative is greater than 0. Okay. And then what do we want to show? So I want to show that for every x1 and x2 in the open interval a comma b, if x1 is less than x2, then f of x1 is less than f of x2. Okay. So this is what I want to show. Once again, I'll have to define these variables again. So I'll define that x1 and x2 be any two real numbers in the open interval a comma b. And of course, we can assume over here that x1 is less than x2. x1 is less than x2. Now, this is a very, very critical point. At this point, we'll have to apply the mean value theorem on f. So I'm going to say I'll apply the mean value theorem on f on the interval. This is very important, on the interval x1 comma x2. This is extremely, extremely important, and here's why this is important. Okay, the reason why I've seen a lot of students will say that I'll apply the mean value theorem on f on the interval a comma b rather than the closed interval a comma b rather than x1 and x2. Now, why is this wrong? Two reasons why this is wrong. The second one is the more important of the two reasons. But firstly, if you go back to the question, you don't even know if the function is defined on at a and b. So there is no way you can apply the mean value theorem on f on at a and b, because, well, the function is defined at a and b. So there's no way to apply the mean value theorem on the closed interval a comma b. But that's not really the logical reason why. I mean, it's one of the reasons, but really the logical reason over here is that your end goal is to show that f is increasing. And if we apply the mean value theorem on f on the closed interval a comma b, what you'll get at the very end is that f of b minus f of a divided by b minus a is greater than 0, which is equivalent to saying that f of b minus f of a is greater than 0. And you'll get from here that f of b is greater than f of a. And this won't prove anything, because the only thing that you've proven by applying the mean value theorem on the closed interval a comma b, given that you can actually apply it over there, is that the right endpoint, in other words f of b, is greater than the left endpoint, which is f of a, which is not what you want to prove. What you want to prove is that no matter what 2 points you pick on the open interval a comma b, the value of the function at the larger point will always be greater than the value of the function at the lesser of the 2 points. That is the idea behind this proof. And by applying the mean value theorem on x1 and x2, where x1 and x2 are any two arbitrary points on the open interval a comma b, I'm precisely doing that. What I'm doing is that it doesn't matter what x1 and x2 is. They are completely arbitrary points coming from the open interval a comma b, and you'll see that I'll get the conclusion at the very end over here that f of x1 is less than f of x2 for any arbitrary x1 and x2 in the open interval a comma b. So, well, let's go ahead and apply the mean value theorem on f. So first of all, clearly note that so the first thing we need to do is verify the hypothesis. So I'm going to begin by verifying the hypothesis. So once again, just to remind you, we need to verify that f is continuous on, well, in this case, the closed interval x1 and x2, and it's differentiable on the open interval x1 and x2. So first I'm going to verify differentiability. So I'm going to say note that as the open interval x1 comma x2 is a subset of the open interval a comma b, and because by assumption f is differentiable on the open interval a comma b, f must also be differentiable on the open interval x1 comma x2. So clearly, as well, this is a subset of each other, and by assumption we know that the f is differentiable on a comma b, open interval a comma b. Thus x1 comma it must also be differentiable on the open interval x1 comma x2. So that's the first part. Now we need to verify continuity, and this is where it gets sometimes a little bit tricky. So since f is differentiable on the open interval a comma b, it must also be continuous on the open interval a comma b. So you can verify this. Uh, Differentiability implies continuity. So if a function is differentiable on a particular interval, it must also be continuous on that interval. The opposite isn't true. Continuity does not imply differentiability. A very the most direct refutation you can give is the absolute value of x. It's continuous everywhere, but it's not differentiable at zero. So yeah, but differentiability does imply continuity, and since the function is continuous on a comma b, then as once again we have x1 comma x2, the closed interval, x1 comma x2 is a subset of the open interval a comma b. F must also be continuous on the closed interval x1 comma x2. And now we're almost done. So we have verified the hypothesis. We can say thus, by the mean value theorem, there exists some point on the open interval x1 comma x2 such that f prime at c is equal to f of x2 minus f of x1 divided by x2 minus x1. But notice that since okay, so this doesn't really have to be a part of the proof, but I'm just going to state this over here. Since c is actually coming from the open interval x1 comma x2, which is a subset of the open interval a comma b, and we know that for any point on the open interval a comma b, the derivative must be greater than 0. So this is f prime of c. This is the derivative at some point on the open interval a comma b. So this must, by our assumption, must be greater than 0. This must be greater than 0. Why? Because at all points on the open interval a comma b, the derivative is greater than 0. C is a point that comes from the open interval a comma b. Thus, the derivative of the function f at c must be greater than 0. Yep, so now we're almost done. All we need to do is multiply this x2 minus x1 on both sides, or we can just multiply x2 minus x1 on the right hand side. So what we'll get is f of x2 minus f of x1 from here must be greater than 0, and this finally implies that f of x2 is greater than f of x1, which is precisely what we wanted to show. This completes the proof. Remember, our goal was to assume that x1 is less than x2, which we did, and thus show that f of x1 must be less than f of x2, which we have shown. F of x1 is less than f of x2. And this is the proof that shows that basically proves that a positive derivative implies that the function is increasing. Now you can see over here that this proof actually works. I mean, if you had, instead of x1 comma x2, if you would have just used the closed interval a comma b, the proof wouldn't have worked. Precisely because of the reason that I just told you, because your conclusion would have been f of b minus f of a divided by b minus a is greater than 0, and you would have gotten that f of b is greater than f of a, which is something you don't want to show. On the other hand, what the proof that we have just written, what this shows is that for any arbitrary points x1 and x2 that you pick on the open interval a comma b, you are always going to get that f of x2 is greater than f of x1, given that x1 is less than x2. So yep, this is the proof. As a challenge, what I will leave you with is, if I just modify this question a little bit, what I would ask you to do is prove this. Instead of saying that the derivative is positive, let's say that the derivative is now negative, and what I want you to do is prove that f is decreasing on the open interval a comma b. You will have to come up with the definition of a decreasing function, like what does it mean for a function to be decreasing. And you will still be using the mean value theorem, and you'll see that the rest of the proof pretty much remains the same. Yep, so do let me know in the comments down below if you were able to solve this question for a decreasing function. And yep, I'll see you in the next video.